Section 11.6, Natural Logarithms. Okay, so in this section we're going to look at a new kind of logarithm where the base isn't base 10, but the base is a number called e. So this is a natural logarithm. A natural logarithm is a logarithm with a base of e, and we write the natural log of a to represent log base e of a. So just like the common log where we write log of some element, let's say it was x, that's the same thing as the log base 10 of x. So when we didn't write a base, it was base 10. Here they're saying if they write the ln instead of the log, that we should take that to mean that the base is e. And e is approximately 2.7183. So this is also a type of log that's on our calculator, which is one of the reasons it's important. So you have your log key right here, which we use for the log base 10, and right below that you have the ln, which is used for the natural log. So this is another one that we can use on our calculator. And a lot of the growth and decay models that we work on end up kind of naturally having a base of e, and sometimes it's nice if the log you take has the same base as the base of your exponential function. So let's get a little bit of mechanical practice with using this new base. So look at these examples. Simplify if you can, otherwise use a calculator to approximate to 3 decimal places. So try and determine what is the natural log of 37.28. So basically we'll be able to do this without a calculator if the inside is some power of e, and this one is not. So when it's a messy one, I'm just going to go to the calculator. So I'm going to put my approximation symbol, and I'm going to try and approximate that as requested to 3 decimal places. So let me bring the calculator in, and I'm just going to enter that in using the ln key, which again, just bring that up real quick. Right underneath the log you have the ln key. So I'll press that, and we get our ln, and then 37.28 is the input, and we get our answer. So 3.618 would be my 3 decimal approximation to that. And just to kind of remind you of how logs work, let's say that we're trying to work this out. What is the natural log of 37.28? Then one of the things we might do is remind ourselves that's a log base e of 37.28, and we might say, well, I don't know what that is, so let me set it equal to k. And if we looked at that for a moment, you might remember the exponential check on that is the base to the other side, or the base raised to the other side, should be equal to the inside. And we've just decided that the answer to this is about 3.618. So if that's correct what the calculator is doing, then if I take this number e and raise it to the 3.618, then I should get this 37.28. So let's try that and see if our answer is making sense. If I take e, 2.7183, and raise that to the answer I got from my calculator, which is about 3.618, then if that's working correctly, that should be 37.28. And when I do that, I get 37.26, so that's super close. The reason it's not working out exactly is because this is an approximation of e, which means it has a little error in it, and I rounded off this exponent. The answer to a log, remember, is an exponent, so I brought in a little error there. But when it comes out so close to what I was expecting it to be, I would say that seems to be a good check that the calculator is giving us the right answer. Alright, now let's look at some where we can actually go ahead and simplify them without the calculator. What is the natural log of e to the 6? So there's a couple ways that we can handle this. One of them would be to use the exponent rule that says you can bring that exponent out front. So I'm going to go ahead and do that and say this is 6 times the natural log of e. And then I want to think about what is this natural log going to be, and to do that, let me write out the base. We won't have to do this all the time, but since it's new, I think we should do it here. So we have the natural log of e is the log base e of e. And one of the things we saw earlier is that any logarithm function is an inverse function to an exponential function. And if you get the log's base and the base of the exponential to be the same, those things cancel out. So we should just get a 6 there. And in fact, if I thought about that at the beginning, I could have done it then too. A natural log is a log base e, So the base of the log should cancel with the base of the exponential, leaving just that exponent, which would be a 6. And then let me go ahead and show you that on the calculator as well. So if I take the natural log of e raised to the 6, so I have right above the division key I have an e key, so I'll hit second e and then raise that to the 6th power. According to our work, that should just be a 6. And press enter, we get a 6, so it does seem like that works. So let me go ahead and box these answers so those are clear. And then just one other thing to look at this. Let's say we were a little confused about what this was. Another thing we could do is say this is the log base e of e to the 6, and we don't know what it is, so let's call it k. And then to try and figure out what that value of k is, we could rewrite this as an exponential form. So we would take the base of the log to the other side, which is that k, and then that should be equal to the inside of the log, which is e to the 6. And then you'd say, what value of k makes this work? Well, if the bases are the same, the exponents have to be the same as well. So if you followed that pattern, you'd get k equals 6, which is also what I got here. So several ways that we can work this out, and 2 of them not involving the calculator at all. So what I want you to see here, and it's the one I'm going to use on the next couple, is that if I can write the inside as base e, then because the natural log is also base e, then the inverse nature of logarithms and exponentials will cancel the log and the exponential base, just leaving the exponent. So if I do this one, this is the natural log of 1 over e, but 1 over e is the same as e to the negative 1. Remember, a negative exponent creates a reciprocal. So now I have a log that's base e and an exponential function that's base e, so the log and the base e would cancel, and I'd be left with just the exponent, which is negative 1. And I'll show you that on the calculator in a minute to verify that that really is working out, but let me show you one more first. On this one, I again want to write the inside as e to some power. So we're trying to think of how can I write the square root of e as e to a power. For that, we want to remember that e to the 1 over n, or actually really anything to the 1 over n, would be the nth root of that thing. And in this case, we have a square root, and a square root is the same thing as using an index of 2. So that means that it's also the same as having e to the 1/2. So I could write the square root of e, which has an index of 2, as e to the 1/2. So I'm going to do that right here. And that is an important thing to remember, that another way to write a square root is that thing raised to the 1/2 power. And the important thing about doing that here is now I have a natural log that is base e and an exponential function that's base e, and so the natural log and the base will cancel, and all that should be left is the exponent. So I should get 1/2 for this answer. So we're basically done with those, and it said to do them by hand if we could, and then use the calculator otherwise. We were able to do these by hand, so they are finished. But let me go ahead and verify both of those on the calculator just as a check. So I have the natural log of 1 over second e, and I get negative 1. And then I have the natural log of the square root of e, and end the parentheses on the square root, and end the parentheses on the natural log. And if we did this correct, we should get a 1/2 on the calculator. And we get 0.5, which is indeed a 1/2. So again, the way we really want to do it is realizing that the natural log will cancel out with a base e, just leaving us with the exponent. That's the inverse nature of logarithms and exponential functions. But we can verify those on the calculator since the natural log is one that can be entered in. Alright, continuing on in section 11.6, we're going to look at solving some equations either by using natural logs as a tool to help us solve, or solve equations that already have a natural log in them. So let me go ahead and show you these examples. So solve each of the following and round our solutions to 4 decimal places. As soon as we see that as part of the directions, we know that the calculator is probably going to enter into the process at some point. So here we have 3 times e to the x equals 85. And just like we saw in the previous section, 11.3, if you're trying to solve for an exponent, then the first step is to get the base by itself. So since our base e is being multiplied by the 3, my first step would be to try and get rid of that 3 by dividing 3 into both sides. So when I do that, that cancels on the left and I get just e to the x. And on the other side you might be tempted to go to a decimal, but I would recommend just leaving that as a fraction. I'm writing it like this in parentheses with the 85 thirds because then if I write it as a decimal, it's going to get rounded. And if I'm going to leave it as a fraction, I'm probably going to enter it in the calculator at some point, and this is the way it would look when it gets entered in. Once you have the base to the same, or the base by itself on one side, you want to get that exponent by itself, or actually brought down from the exponent. And the tool that we have for doing that is taking a log. So we could take the log of both sides, and that would work. But it would be a little easier and faster on the algebra if the base of our log matches the base of the exponential function. So since I have a base e, I'll take the natural log of both sides, and that will allow these to cancel, and that's going to save me some steps on the algebra. Again, if the base of the log matches the base of the exponential, the inverse nature of those two functions means they'll cancel out, just leaving the exponent. And so x would be equal to whatever the ln of 85 thirds is. And so then I'd just go to the calculator on that. So I'm going to pull that in. So I want the natural log of 85 over 3, and I get approximately 3.344 and a 0. So that would be to 4 decimal places as requested. And whenever you want to check one of these answers, you can plug your solution in for the x on this side and see if you end up with the right side. So 3 times e raised to the answer I just got. Let me just point out what I did there. The answer key is above the negative key, and if I use that, then instead of having to type that decimal in again, it automatically will put that decimal in that spot. So I'm doing 3 times e raised to the 3.344038968, and if that's really a solution, these two sides would be equal. So this left side should equal the right side of 85, and it does. So that's a good sign that I've done things correctly. Alright, let me go ahead and move on to part B. In this one, we're starting out with a log already, a natural log to be more specific. And we've solved this type of equation again, also back in section 11.3. The only difference now is the type of logarithm we're using. And our goal back then was that we could solve these if we could get the log by itself. So we want to isolate that log, and that means we need to get rid of the 2 and the negative 3. So the first thing I would do would be to add 3 to both sides, and that would cancel those 3's off. And then I have 2 times the natural log of 5x, and that would be equal to 4, adding the 1 and the 3 together. Still trying to get that log by itself, so I want to get rid of that 2. So divide both sides by 2. So those cancel out. And now I have the natural log of 5x equals 2 by dividing, simplifying there. 2 goes into 4 twice. So at this point, I'm kind of stuck as far as working with the logarithm. So what I'm going to do is switch over to exponential form. I think that might be a little easier if I can see the base. So I'm just going to write this out as log base e, which means the same thing as natural log of 5x equals 2. And then I'm going to switch this to exponential form by saying the base of the log raised to the other side of the equation equals the inside of the logarithm. So it looks like 5x is equal to e squared, and that's great progress, but we're not trying to figure out what 5x is, we're trying to figure out what x is. So just one final step here. Get that x by itself by dividing both sides by 5, so that cancels the 5 out over here on this side. And then we could say that x would be equal to e raised to the second divided by 5. And I wrote it again in this kind of odd way because that's the way we could enter it into the calculator. And we're going to want to do that because we were asked to round our solutions to 4 decimal places. So let me bring the calculator in. We'll take care of that calculation. So we want e raised to the second, and then that's going to be all divided by 5. I use the parentheses just to make sure that the 5 is happening after the exponent, but order of operations exponents would have come before division anyways, but it doesn't hurt to kind of emphasize that with parentheses if you'd like. So I get 1.4778. And that should be my answer. If we wanted to, we could go ahead and check that by entering that x in right here and doing the whole left side on the calculator, and if we have done the correct thing, it'll turn out to be a 1, which matches the other side. So let's see, the left side is 2 times the natural log of 5 times the answer that we just got, this 1.4778, and so on, and then minus 3. That's the left side of our equation with our solution plugged in for x. So if we've done things right, that should be equal to 1. So let's go ahead and see how that turns out. And we do in fact get 1. So that kind of confirms that we have done this properly. So let me bring this back over. Now that we've checked that answer, I'll go ahead and box it. Alright, let's look at another example. This time we have an exponential function like we did on the first one. So we want to try and get this exponent down, the variable down from the exponent. But to do that, you have to isolate the base first. So I got to get rid of this 7. It's connected to the base by multiplication, so I'll divide both sides by 7. Those cancel on the left. And I get e to the 2p plus 10 is equal to 100 over 7. And again, I don't want to go to a decimal there. That's going to bring in rounding error, so I'll just leave it as a fraction. And when I want to get a variable down from an exponent, the trick to that is taking a log. I have to do that on both sides to keep things balanced. And I chose the natural log because if the base of the log matches the base of the exponential, then those cancel out. And that would just leave the exponent, which would be 2p plus 10 equals the natural log of 100 over 7. And then I just need to try and get this variable p isolated, so I need to get rid of the 2 and the 10. Get rid of the 10 by subtracting 10 from both sides. I'll just write that right there. And then get rid of the p by dividing both sides by 2. Let me write out what we have here. So 2p equals the natural log of 100 over 7 minus 10. And then I want to divide by 2 here to cancel that off and get p by itself, and divide the whole other side by 2 to make that work. And then finally, they want an approximation. So let me go ahead and enter that into the calculator, all of this, and make sure that I get a decimal to 4 spots. Now when I enter this in, there's one thing you have to be careful with. If your numerator or denominator on a fraction you're going to enter into the calculator has more than one number in it, then you should put that numerator or denominator in parentheses when you go to the calculator. So when I enter this in, I'm going to put that what appears to be an extra set of parentheses around the numerator, but if I forget those, then the order of operations will get messed up and it'll divide the 10 by the 2 rather than the whole numerator by the 2. So the parentheses are important in that regard. So let me go ahead and bring in the calculator again, and let's try and enter that in. So parentheses around the top, natural log of 100 over 7, that ends what's inside my natural log, so I end those parentheses. And then I have the minus 10. That ends my numerator, so I end those parentheses, and then all of that's supposed to be divided by 2. You might get tempted when these things get messy to start entering them in the calculator in pieces, but if you do that, you end up having to round and carry messy decimals through a bunch of steps, and that brings in error of its own. So I would encourage you to try and write the whole thing into your calculator at once, and then just get a single answer that you could then round. So this would be negative 3.6704. Now it didn't say a 4, it was a 3, but followed by a 6, so I would round up. So this is the first time we've got a negative answer, so that might just feel a little bit weird. So maybe just like on the others, it'd be a good idea to check. So I'm going to take 7 times e raised to, anytime your exponent has more than one piece to it, you should put that in parentheses. So 2 times the answer I just got plus 10. So if that answer of negative 3.6703 and so on is correct, then when I evaluate this left side, I should get the right side, which is 100. And I get 100. So even though that negative may have come as a little bit of a surprise, it looks like it really is indeed the correct answer. And it kind of makes sense, because if you had e to the 10, that would probably be a big number, much bigger than 100. So you need that p to be negative to kind of reduce that exponent a little bit, so you just get 100 instead of a gigantic number. Alright, so since that answer checked, let's go ahead and box it. And that finishes off that example. Alright, as we continue on, I just want to show you a couple more examples on this page where some tricky things come up. So let's start off with D here, where we have e to the 2x minus 3 times e to the x equals 83. So this is something we haven't seen yet, where we have the base show up twice. But remember our rule that if you have the same base, x to the m, times the same base, x to the n, the rule says add the two exponents together. So I can apply that whether the exponent is x, 7, or even e. So when I try and do that, I get e raised to the 2x minus 3 plus the exponent from the other base, which would be the x, is equal to 83. So when you have the two bases like that and they're multiplied together, just go ahead and add their exponents, and that gets you down to a single base, which is going to make this easier to solve. Since there's a 2x and an x, I'm going to go ahead and combine those like terms. So 2x plus x would be 3x, and then we still have the minus 3, and on the other side we have the 83. Once you get an equation to the point where you have just the base by itself, then you want to try and get the variable out of the exponent, and the trick to that is taking a log of both sides. And that log could be a natural log or a common log, but it always reduces the algebra steps if the base of your log matches the base of the exponential. We also are going to have to go to the calculator eventually, so we really only have two choices, natural log or log base 10, which is the common log. But since this has an e for the base on the exponential, I want to do ln, which also has base e. Because when the base on the log matches the base on the exponential, we get a cancellation there, and all that's left is our exponent, 3x minus 3, equals the natural log of 83. It doesn't need to be in parentheses there, but in the calculator it always is, so I'm going to go ahead and show it that way so it matches up a little better with our calculator work. And now I'm going to just try and solve for x. So I'll add 3 to the left to cancel those, so I'll add 3 to the right as well. That gets me to 3x equals the natural log of 83 plus 3. At this point it's actually kind of nice to have those parentheses there so you know that only the 83 is in the log and that this 3 is on the outside. It's a separate piece. And then we want to get rid of this 3, so divide both sides by 3. These 3's cancel out and x is by itself. And at that point we go to the calculator. But like I mentioned in the last problem, if your numerator has more than one term to it, then when you go to the calculator you'll want that in parentheses, so I'll go ahead and show those here. Those parentheses are not required to write down, but they are going to be necessary in the calculator. So let's go ahead and take a look at that. So we would open parentheses for the numerator, and we would do the natural log of 83, that's the end of our log, so close those parentheses, plus 3, which is also in the numerator, but that's now the end of the numerator, so close parenthesis on the numerator, and then divide that by 3. So x should be approximately 2.4729. I believe our rounding directions were 4 decimal places. And yes, I just double checked that. That's correct. So we want 2.4729, 4 decimals. Almost had to round up, but that is a 4, so we don't round up there. And all these are a little bit messy, so I think it's a good idea to check them. So let me go ahead and enter that equation into the calculator. On the left, I have e raised to the 2 times my answer minus 3, and then that's times e raised to my answer. So what I'm doing there is just plugging my answer in for that x and that x. When a exponent has multiple terms, you need to put those in parentheses, so I did that. And if this really is the answer, then since I plugged it into the left side, it should be equal to the right side, which is 83. And there we go. Alright, let's go ahead and try another one. I guess just real quick, since we finished that off, I'll box it and make sure it's clear where my answer is. And then let's continue on. So 2.4x equals 63.5. This actually is going to be a very fast one. We already have our base by itself. Our base happens to be a decimal, but that's not that big of a deal. So once we get our base by itself, we want to bring the variable down from the exponent. The step to do that is to take the natural log of both sides. Actually, it's to take any log of both sides, but I do want to use one that's in my calculator. There honestly is no real advantage to using natural log versus common log on this one. Either one of them would work. I am in the habit, because of my background, when I have the choice, to do natural log, and if for no other reason it's 2 letters instead of 3, it saves you a tiny bit of time. It's really not a big deal. But when you take that log, the reason we're doing that is it allows us to bring that exponent out to the front. So if we do that, we'd have x ln of 2.4 is equal to the ln of 63.5, and we want this x by itself. The natural log of 2.4 is multiplying the x, so if I divide both sides by natural log of 2.4, then those would cancel off. Have to do that on the right as well to keep things balanced. So it looks like x is the natural log of 63.5 divided by the natural log of 2.4, and they want a decimal, so I'm going to go ahead and bring in the calculator at this point. And on the top, I have natural log of 63.5. Make sure I end parentheses, so that's all that's in the first log, divided by the natural log of 2.4. And if I press enter, I get 4.7415. And I'll go ahead and check that answer for you in just a second, but I do want to show you one other thing while I have this up here. I mentioned that we could have used natural log or common log, so let me enter this again, but using the common log button. So common log of 63.5 divided by the common log of 2.4. And if I'm telling the truth there about it not mattering what type of log you use, I should get the same answer. And there we go, it is in fact the same. So you can make the choice whether you want to use natural log or common log. It is worth noting, I suppose, that ln of 63.5, the numerator, is different from common log of 63.5 if you use the other one. However, the difference between the natural log and the common log will cancel out in that fraction, and you'll still get the same answer. So you can't just pick whatever, wherever. You have to make a choice, and if it's natural log, fine. If it's common log, fine. So don't mix them, but you can pick whichever one you want. It'll still work out. And speaking of working out, let's just verify that it in fact did work out. So 2.4 is my left side. Raise that to my answer. So my most recent answer is not the answer to the problem. The answer to the problem was this 4.7415, so let me just enter that in. Now because I'm entering the decimal and not going the whole way, I won't get exactly 63.5. I should just be close. 63.499, that's certainly close to 63.5, so that's just because of the rounding error that was brought in when I went to 4 decimal places. Alright, one final example here. Let's look at the intersect on the graphing calculator to solve 3 times the natural log of x plus 3 equals 0.7x plus 2. So this turns out to be an equation that if we tried to solve it completely algebraically, we'd get stuck on. But on equations like that, we always have the option of putting the left side into y1 and the right side into y2, and then looking for where those graphs intersect to find the solution, something we've done several times before in other chapters, and this chapter in fact. So let's go ahead and do that. I'm going to go into the y equals menu. I happen to have a couple old functions there, so I'll clear those out. For y1, I'm going to do the left side, 3 times the natural log of x plus 3, and press enter. So I've got the left side for y1, and for y2, 0.7 times x plus 2, and press enter and lock that one in. Now I don't know where the intersection is going to be, so I'll start off by hitting zoom and standard, which will give a negative 10 to 10 and negative 10 to 10 window for both x and y. And we'll see our graphs. There's the log graph. There comes the line graph. So this is interesting. It looks like there's more than one answer. I see an intersection here and an intersection there. So it looks like there's going to be 2 answers to this, and we'll write both of them down. So we're going to have x is approximately equal to, and then we'll have or x is approximately equal to, and give a second answer. So this is an interesting one. Let me go ahead and show you how this works. We go into the calc menu, and we choose intersect. And one of the things that we've seen with this before is it's going to say, is this your first curve? Yes. Is this your second curve? Yes. And we haven't paid that much attention to this, but what is your guess? Well, if you guess something close to this one, it'll find that one. If you guess something close to this one, it'll find this one. So I'm going to go from left to right and use the arrow keys to get the little flashing cursor close to where it looks like the intersection is, and then I'm going to press enter, and because I was close to that one, that's the intersection it found. And that x is approximately negative 1.685, and let's see, the next digit is a 6 followed by a 3, so that would stay as a 6. So now there's one of the intersections. Now we want to find the other one. So to find the other one, I'm going to go to calc again, so second calc, choose intersect again. First graph, yes. Second graph, yes. But I don't want that to be my guess because I'll get the same answer again. So I'm going to use my right arrow key to move over so that intersection and that cursor are together. I'm going to press enter, and now it found this one. And so it's going to find the one that's closest typically. So you want to get, using the arrow keys, pretty close to where they intersect, and then go ahead and press enter on that guess. So 7.019, and then after the 9 we have a 3, but it's followed by a 7, so we'll make this a 4 right there. So two different solutions to this. And that can happen sometimes when you have a graph that curves. It's capable of hitting another graph more than one time, and so we're seeing that in this case. Since that is the first time we've seen that, I'm going to go ahead and check these answers for you. This is a little bit of a pain to check, but I'll go ahead and show you. So what I need to do is enter in the first one using this value. So 3 times the natural log of x plus 3. So my x is negative 1.6856 and then plus 3. And I press enter and I get about 0.82. So if this is really a solution, I should get the same thing on the other side. So 0.7 times negative 1.6856 and then plus 2. And again, if it's really a solution, the two sides should be equal, so I'm expecting about 0.82 again, and I get 0.82. They're not exactly the same because I'm using a rounded answer. If I use the answer key, which I don't have available in the graphing situation, but if I entered all the decimals, they should be exactly equal. But not only is this one an answer, so is this one. So let's test the other one as well. 3 times the natural log of 7.0194 plus 3. So on the left side I get about 6.91. Let's try the other side. 0.7 times 7.0194 plus 2. If this is really an answer, the two sides should be equal, so I'm expecting about 6.91 again. And I did in fact get that. 6.9135, it's just that's a 6 versus an 8. And that's not because it's not really a solution, it's because it's a rounded solution. So that's kind of a new one there where we see that it's possible to get more than one point of intersection on your graph. When you see that, you're just going to have to use the intersect feature twice. Just make sure your guess is close to one of the intersections to get it, and then when you do it again, move the guess over near the other intersection. So both of these would be answers. If this were to occur on MyMathLab, just remember that you would enter the first answer and then a comma and then the second one, and you should see that in the directions to enter your answers separated by a comma.